Swayam Prabha. Digital India. Educated India.
Hello learners, I welcome you back to our Microeconomics and its Applications course. We are into the third unit of this course and today it is our second lecture. I am Dr. Aparna Samudra, who is the course coordinator as well as the presenter for this lecture. My dear students, just to give you a small recap, what we have been doing in Unit 3 is we are talking about production function, where we are saying that production is transformation of inputs into outputs. We want to understand that how does the output change when we change the inputs which are available with the producer. And for that, we have been talking about two types of production function in two different types of time period. One is called as a short-run production function and other is called as a long-run production function. What is the difference between short-run and long-run? In short run, we say that if we are taking two inputs which we are using or the producer is utilizing to get any output, out of these two inputs, one remains constant and the quantity or the number of the other input changes. So the input which is changing, we defined it as the variable input, and the input for which the amount or the quantity remains the same is called as the fixed input. So what we understood was that in short run, one variable is fixed and other variable is constant, or variable is constant. So one is fixed, other is variable. So two types of factors of production are there: variable factor of production and fixed factor of production. We understood the law of variable proportion in it, wherein we saw that how if we keep one factor of production constant or fixed and we change the number of the variable input, how does the output change? For that, we understood total product, average product, and marginal product, and we saw the behavior of all three types of products as the variable input or more and more of the variable input is applied on the same amount of the fixed input. That is what we did in the previous lecture in the short-run analysis of production function. The other type of production function we said is long-run. What is long run? In long run, we had said that if there are two inputs which are being used to produce some output, the firm has a choice to change both these inputs. That is, the number of the quantity of both the inputs. Let us say we are taking labor and capital, then labor can be changed as well as capital can also be changed. That is a situation of what we call as long run. So today, the concentration of this lecture will be on the long run analysis of the production function. And for that, we will be understanding the concept and properties of isoquants. Thereafter, we'll understand the meaning of what we call as marginal rate of technical substitution, which is also called as MRT'S. Then we will understand what do we mean by returns to scale and what are the various types of returns to scale. So let us go ahead with today's lecture. As I just told you that this lecture will be concentrating on the production in the long run, wherein we are considering that both the inputs, that is labor as well as capital, have become variable. That is, we are able or a firm is able to change the number of labor as well as it is able to change the amount of capital. So both the factors of production or inputs have become variable. Now the question comes is, I as a producer can change labor as well as I can change capital. So the question is, how do I determine that what should be my optimal combination of labor and capital? For that, we use what we call as production isoquants. What is an isoquant? Isoquant is basically a locus of all the technical efficient methods or all possible combinations of inputs for producing a given level of output. That is, when we get various combinations of labor and capital which can be utilized to give the similar level of output, when we join these combination, the curve which we get is called as isoquant. Let us see it further. An isoquant, it is also called as an isoproduct or equal product, or many times it is very similar to the indifference curve which we done in a case of consumer behavior. So in layman's language or in simpler terms, you can say that isoquant is similar to the indifference curve of a producer. Iso basically means similar, equal, equal product curve. So an isoquant or an isoproduct curve shows, what does it show? It shows the various combinations of the two variable inputs which are resulting in the same level of output. That is, different combinations of labor and capital which are generating the same level of output. When we join them together, the curve that we get is called as an isoquant, equal product. That is, in this particular curve, all the combinations of the two variable inputs are going to give the producer the same level of output. Right? So it is also defined as a curve which is passing through the plotted points, representing all the combinations of the two factors of production which will produce a given output. That is, if you plot it on a graph where you are taking variable factors on the x-axis and the y-axis, so the different combination of both the variable factors which are giving the same level of output, when we join them together, this curve is called as an isoquant. Whenever we are talking about isoquants, there is an important assumption which we make. What is this? This assumption says that the two inputs can be substituted for each other. That is, you can, instead of having less capital, you can have more labor. Right? So capital and labor can be substituted for each other. However, the proportion of labor and capital will have to remain the same. Okay, for example, if we are saying if a company decides to reduce labor, okay, now if it is reducing labor, it will increase the amount of machinery or the capital it is using. Okay, so that it gets the same level of output, and this proportion we say remains the same. Okay, for example, I am giving you this table wherein we are seeing different combinations of pairs of labor and capital which are resulting in the same output. For example, we are saying that you can either have 1 unit of labor and 5 units of capital. This combination is giving you 10 units of output. Right, so this becomes one combination. Another combination we see is that you are using 2 units of labor and 3 units of capital. But again, this particular second combination is also giving us the same level of output, and so on. What do we see here, learners? If you see carefully, as you are increasing the number of units of labor, the number of units of capital that you are using is falling. It is decreasing. So each combination, all the 5 combinations which are listed in this table of labor and capital are producing the same level of output. So in order to increase one particular your variable factor, you have to reduce the other variable factor. Okay, so when we plot this labor capital combinations, all these 5 combinations on a graph, we get a curve, and this curve is called as an isoquant. All of them are giving us the same level of output. Okay, now let us see this graph. For example, I am saying that we are measuring capital on the y-axis and labor on the x-axis. So all these points A, B, C, D, which are lying on this blue curve, which is an isoquant Q1, are showing different combinations of labor and capital. Yes or no? Because at A, the combination of labor and capital is different from the combination of labor and capital at point C. But all these technically efficient combination of labor and capital are producing the same level of output, 290. Another isoquant Q2 is representing a higher level of output, but F and E, even though they have a different combination of labor and capital, but they are producing the same level of output. Similar, we can have another isoquant which is giving you another level of output, even though H and G will have different amounts of capital and labor, but the output that they are going to produce will remain the same. Another interesting thing you must be noticing here is that as we are moving up the curve from Q1 to Q2, Q2 to Q3, the output is increasing. Means a higher isoquant is representing a higher level of output. We will be discussing this when we will be talking about the properties of your isoquants. Okay, now these are some of the types of isoquants that we have. The first is a case where your isoquant is a linear isoquant or it's a straight line. When will be an isoquant a straight line? It will be the case when these two are perfect substitute. These two inputs that we are using in the production of something are perfect substitutes to each other. For example, sugarcane syrup or sugar, both these inputs are completely substitutable. That is, you can completely use sugarcane instead of sugar. There will be no change in the type of taste that you are getting for this product that you are manufacturing. Second type of isoquant is a L-shaped isoquant, as you can say, where the goods, these inputs are perfect complements to each other. That is, there is a fixed combination for which you will be using these two inputs. There is a fixed combination of all the other ingredients that you are using, let us say, to produce juice, and the natural flavoring that you are adding in the production of juice. So there is a fixed combination which you will be requiring to use. Okay, so in that case, when a fixed combination of inputs has to be used, we say that this particular isoquant will be L-shaped. The third type of isoquant is convex to the origin. As you can see, this blue isoquant represented by Q, it is convex to the origin, showing that even though I can substitute labor for capital, but they are not perfect substitutes for each other. There is limited substitutability. Labor may not be as efficient as capital, or capital may not be as efficient as labor in production of something. So even though I want to increase labor, I am reducing capital, but they are not perfect substitutes to each other. So when this happens, our isoquants becomes convex to the origin. These first and the second, where your isoquant is a linear line or L-shaped, these are very extreme cases. Otherwise, the natural cases of having a convex isoquant. Moving on to the second thing is your marginal rate of technical substitution, which is also called as MRT'S. What is this? MRT'S, or marginal rate of technical substitution, is the slope of the isoquant, intending to say that if you have to remain on the same level of output that you are producing, you have to increase. For example, you are moving from one point to another point, or one combination of labor and capital to another combination of labor and capital. If I want to increase the number of labor, I have to decrease the amount of capital. Or if I'm increasing the amount of capital, I have to reduce the amount of labor. So this rate of substitution of capital for labor or of labor for capital is called as the marginal rate of technical substitution. Okay, so MRTS we are saying is the slope of the isoquant, and it is written as MRTS is equal to delta L by delta K. That is, delta L is change in labor due to change in capital. That is, if some amount of labor is removed from the production, then it has to be substituted by the capital to remain at the same level of output. So for reduction in labor of 1 unit, how many units of capital I had to increase? That is measured by your MRTS. So what is marginal rate of technical substitution? MRTS is the slope of the isoquant, showing that how much of one input you have to reduce or you have reduced, and for reduction of that input, how much of the other input you have to use extra. That change is called as marginal rate of technical substitution, which is change in one input divided by the change in other input. That is called as marginal rate of technical substitution. Delta L by delta K, also we say it is marginal product of labor divided by the marginal product of capital. Okay. Now this particular figure that you see is indicating an isoquant map. What is an isoquant map? When you are showing or when you are plotting different isoquants on the same two-dimensional figure, this is called as an isoquant map. A higher isoquant is showing a higher level of production. Very similar to the indifference map, curve map that we did. So when on a two-dimensional plane, we are plotting different isoquants, is called as an isoquant map. Each isoquant is showing you a fixed level of output or a given level of output which is being produced. Now let us move to what are the various properties of isoquants. You will find again a lot of similarity between these properties of isoquants and the properties of the indifference curves. The first we have seen is that the isoquants have a negative slope. Negative slope means they are sloping downwards. Meaning to say that if you are increasing the quantity of one input, you have to reduce the quantity of the other input. So if you are using more labor, you have to reduce the amount of capital. If you are using more capital, you have to reduce the amount of labor. So therefore, isoquants have a negative slope. Second, isoquants are convex to the origin. This convexity happens because of your diminishing MRTS. That is, we have just seen marginal rate of technical substitution is the rate at which you are substituting one input for the other input. They become convex because these two inputs, labor and capital, are not perfect substitutes to each other. So as and as if you are increasing the number of labor, the amount of capital that you are reducing, that number, that change of capital will keep on declining. Meaning to say that because of diminishing marginal rate of technical substitution, your isoquants are convex to the origin. So if initially for one extra unit of labor that you are taking, you were reducing 5 units of capital, later on as you have more and more of labor, this reduction in capital will decline. That is, for the second unit, maybe you are willing to not give 5 units of capital. Maybe you are willing to give up 4 units of capital. Why? Because labor and capital are not perfect substitutes to each other. Therefore, isoquants are convex to the origin. Then isoquants cannot intersect or be tangent to each other. Why? Because if two isoquants intersect or become tangent to each other, means there is one combination of labor and capital, or the two variable inputs, which is lying or which is giving you different levels of output. which is not possible. Therefore, isoquants cannot intersect. Then, as I've told you earlier also in this lecture, a higher isoquant represents a higher level of output. Okay, we have just seen in the indifference map, or sorry, isoquant map also, this particular property. Now, after understanding the isoquants, let us move to the law of returns to scale, wherein we are trying to understand that if we are changing the quantity of both the inputs, you are increasing labor, we are increasing capital together, then how will my output change? How much will my output change if I'm changing both labor and capital? That understanding we get when we see the law of returns to scale. Scale basically means size. So if we are changing the size, what returns the firm is getting because of that is studied in the law of returns to scale. Why size is changing? Because you are increasing the amount of both the inputs. So with an increase in amount of both the inputs, the firm's size will increase or decrease, whatever is the case. So let us have a look for what is law of returns to scale. As I just said, in long run, a firm has enough time to change amount of all the inputs. If we are taking two inputs, labor is also increasing or changing and capital is also changing. So the long run production process is therefore described by the concept of returns to scale, as I've told you. Basically, by understanding this, we see that because of the change in size which has happened because we are changing both the inputs, how does the output change? Okay, so returns to scale is basically the resulting increase in the total output as all outputs increase. How does my output increase? When I'm increasing the quantity of both the inputs or all the inputs. So law of returns to scale is explaining the behavior of output in response to a proportional and simultaneous change in inputs. That is, you are changing the inputs at the same time. Both the inputs you are increasing at the same time proportionately. How will my output change because of that is what we study in this returns to scale. This is what returns to scale explains. Okay, now let us have a look at this. For example, I'm saying if all the inputs in the production process are doubled, I am doubling the amount of labor, I am doubling the amount of capital. Okay, I was earlier using one labor, one machine. Now I use two labor, two machines. Three things will happen because of this increase in the inputs simultaneously and proportionately. Three things will happen to the output. What three? One, your output can increase more than double. Your output more than doubles. You changed, instead of having one labor, one machine, you had two labor, two machines. So you saw your output was initially, let us say, 10 units. With doubling of labor and capital, you see your output coming out to be 25. This means that your output has more than doubled. Okay, so when you double your inputs and your output increases, it changes more than double. Then we call it as increasing returns to scale. Other thing which can happen is you have doubled your input and your output exactly doubles. You doubled your labor and capital. Output also doubled. Okay, from 10 your output became 20. So doubling input led to doubling of output. That is called as constant returns to scale. Third situation, output can less than double. That is, output will increase, but it will be less than double. You had two labors and two machine now instead of one labor and one machine, but your output instead from 10 it went up to, let us say, 18. So it of course went up, but less than double. A double would have been 20. Now it has increased by 8 units. That is, it has increased but less than double. That is called as decreasing returns to scale. So three types of returns to scale can take place: increasing, constant, and decreasing. Okay, let us have a look at this graphically. For example, these are the three isoquants that we have: x, 2x, 3x, meaning this is one level of output, this is the double of this output, this is three times the original output. X, 2x, 3x. Okay, representing x, this x represents you are using L amount of labor and K amount of capital. 2x is showing, now what is happening? Let us see here. Okay, now you are doubling your, let us say, doubling your input, labor and capital. So from L, you will go to 2L. From K, you go to 2K. Right? What has happened? Your input has more than doubled. Na? If it would have doubled, you would have been on this isoquant 2x, because this isoquant 2x is the double of the initial isoquant x. But where are you producing? You are producing at a higher isoquant than 2x. Correct? So this means that this is a situation of increasing returns to scale. Because you doubled your input, your output increased more than the double. Right? That is called as increasing returns to scale. Let us compare this case with constant returns to scale. What do you see here? You were probably at x initially, x isoquant, taking one labor, one capital. You double the amount of labor in capital. So you get 2L, 2K. Okay. Which isoquant are we meeting right now with 2L, 2K? You are meeting with this isoquant 2x, which is just the double of the initial isoquant. This means this is a situation of constant returns to scale. That is, you double your input and your output also doubled. Compared to the increasing returns to scale, where we saw output increasing more than double. Let us see decreasing returns to scale. What is happening here? You are initially at x. You double your inputs, labor and capital both. But where is the output? Output is below the 2x. 2x represented what? 2x represented the double the amount of output. But we are producing at a lower than 2x output. Means your output increased but less than double with the doubling of inputs. That is called as decreasing returns to scale. Okay, so when we talk about your laws of returns to scale, we are seeing that your input can be on it. You can see an increasing returns to scale, decreasing returns to scale, or constant returns to scale. Now these returns to scale again can be described using this particular equation. If Q is a function of x and y, that is, your output is a function of two inputs x and y, and both x and y are changed by the amount of k. That is, you are changing x by amount of k and y also you are changing by amount of k. So the new production function becomes f is a function of kx and ky. Now because there is a change in the inputs x and y by k, we are seeing the change in quantity or the output by amount of h. So with a change in inputs by k amount, output changes or the production changes by h amount. So if this change in quantity or output, which is indicating by h, if this h is greater than k, that is, the change in output which is given by h is more than the change in input which is given by k, then we call it as increasing returns to scale. Second situation is the change in output h is equal to the change in input k. Then it is called as constant returns to scale. Third is when the change in output h is less than the change in input k, then it is called as decreasing returns to scale. So by seeing or by calculating how much is the change in output due to the change in input, we can talk about whether the returns to scale are increasing, constant or decreasing. Okay, so quick recap. 3 types of returns to scale we have seen: constant returns to scale, increasing returns to scale, and decreasing returns to scale. Constant returns to scale means a proportional change in both inputs lead to change in output by the same proportion. You change inputs by 10%, output also changes by 10%. Increasing returns to scale, you are changing inputs by 10%, but we see a greater change in the proportionate change in the output. Change input by 10%, output changes by 12%. So change in output is proportionately more than the change in inputs. Decreasing returns to scale, your output changes less than the change in inputs. So what have we done, my dear learners, today? Let us summarize it quickly. We have talked about isoquants. What are isoquants? We said isoquants are those, it's a locus of all those combination of two inputs which give the same level of production. So isoquants are basically used to study the production decision with two variable inputs. It is the downward sloping curve showing all possible input combinations which are used to produce the same level of output. It is also, isoquant is also called as isoproduct curve, equal product curve, or maybe indifference curve of the producer. The slope of isoquant is given by MRT'S LK, means marginal rate of technical substitution for labor and capital, which measures the rate at which the firm has to substitute one input for another to keep the output unchanged. That is, if I am increasing labor, the rate at which I have to reduce capital, that is measured by your marginal rate of technical substitution, and it is the same as the slope of the isoquant. Many times we write MRTS is equal to MPL upon MPK. Okay. A firm in returns to scale can exhibit constant returns to scale, increasing returns to scale, or decreasing returns to scale. So these are the 3 types of returns to scale which a firm may exhibit. So this is with long run production function, the behavior of the output with respect to the change in both the level of inputs. In the next lecture that we have, we will be now talking about that how does the firm decide the optimal combination of the two inputs it has to use. And then we will also be talking about the expansion path. I hope learners, you enjoyed learning this new concept. Till then, happy learning.